Hi, I'm Kirk Weiler, and today we'll be talking about the product and quotient rules in Math 4 Honors. Now, in the last lesson we saw a variety of derivative laws, the most important of which being the power law. We also saw things like the constant multiplier law and the constant additive law and the addition and subtraction laws, none of which we'll probably remember their names, but the power law, of course, we'll remember. Today, we're going to take a look at two laws that allow us to find the derivative of a product and the derivative of a quotient. These are much harder because, unfortunately, the derivative of a product and the derivative of a quotient can't be just found by finding products and quotients. It's really quite unfortunate, but it is what it is. Let's take a look at the product rule. So the product rule has a very strange form. It says, if we've got a function, let me close this thing down. If we've got a function that can be thought of as the product of two functions, let's say f of x and g of x, then we can find its derivative by leaving the second function unchanged and multiply by the derivative of the first function, plus, very important, the first function times the derivative of the second. Pretty confusing, huh? It'd be great if the derivative of f times g was just the derivative of f times the derivative of g, but it simply isn't. Let's try to keep that on the screen so that we can see it for the first problem. One thing to note about products is that products in general are commutative. Whether it's f times g or g times f is irrelevant, and therefore the product rule itself has a lot of commutativity built into it, i.e. you could do the derivative of the first function times the second function first, or you could do the derivative of the second function first times the first function. All of this starts to sound rather confusing if I'm not writing stuff down. So let's take a look at the first exercise, where we've got a function, f of x, that is the product of two functions, 3x minus 2 and 2x plus 1. Let's use the product rule to find its derivative. df dx. The product rule says, take the first function and find its derivative. Well, that function's linear, so its derivative is just 3. And then multiply it by the second function, 2x plus 1. Plus, now we'll take the derivative of the second function, which is 2, and we'll multiply it by the first function, 3x minus 2. That's it. That's the whole product rule. Everything after this is just elementary algebra, which we can easily do by just sort of cleaning this up, right? We can distribute the 3, distribute the 2, and obviously we'll have a final derivative of 12x minus 1. Alright. Now, it's somewhat hard. Whoops, we just lost our exercise. It's somewhat hard to motivate the product rule right now, because we could have done that derivative a different way. And so let's actually do it the different way. One way that we should always be open to attacking problems in math, in general, is by first manipulating the problem. So for instance, one thing we could have done is just multiplied out these binomials, foiling them, if you will. If you were to multiply out those two binomials, you'd have f of x equals 6x squared minus x minus 2. At this point, we could take the derivative from the last lesson by just using the power law. F prime of x will be 12 times x to the first minus 1. And remember, the derivative of a constant is 0. So as long as you've learned the power law and some other ones, we can find the derivative in a different way. So it's kind of tricky. One thing, kind of looking a little bit into the future, so don't worry too much about this right now. Eventually, we will be forced to do the product rule. Let's say we had something like f of x equals x squared times sine x. Now, you may have already learned about trig derivatives, but I haven't taught them in my course yet. Still, you can imagine that at some point we're going to know what the derivative of the sine function is. So to find the derivative of x squared times sine x, we would need to know the product rule. Let's do one that's way more symbolic in nature and one that definitely requires the use of the product rule. In exercise number 2, we're told that we've got some function g of x, and we don't know a lot about it. We do know that g of 5 is negative 2, and g prime of 5 is 3. Then we come along, and you're going to see this happen a lot in calculus. We define a second function in terms of the first. And this says f of x is always x squared times g of x. Doesn't matter what x is. And they ask me then to find, no great shock, the derivative of f at 5. All right. Well, it makes all the sense in the world that we're going to use the product rule here, because f can be thought of as the product of x squared and the function g of x. I haven't left myself a lot of room to circle. So the product rule is going to say, take the derivative of the first function. Well, that's simple enough. The derivative of x squared is 2x, but then multiply it by the second function. We don't know a formula for g of x, so the best I can do is write down g of x plus. Now we're going to take that first function, x squared, and we're going to multiply it by the derivative of the second. The best I can do there is write down g prime of x. That's all I can do. I can't give a formula for it. I just write down g prime. Now the beautiful thing is, to evaluate f prime of 5, all I have to do is know function notation. Right? If I put 5 in for that x, I have to put 5 in for every x I see. So notice, everywhere there's an x, I'm now going to replace it with 5. Of course, to be able to finish this problem off, I have to know what g of 5 is and what g prime of 5 is. But we do know what those are. They're given up here in the problem, right here and right here. So we just have to plug values in. I'm going to do a little bit of arithmetic right here. 2 times 5 is 10. G of 5 is negative 2. Of course, 5 squared is 25. And g prime of 5, according to this problem, is 3. When we work out all the arithmetic, that comes out to being a derivative. Why am I sorry? I'm not sorry. The derivative is the slope. So a slope of 55. Now the other thing the problem asks us to do is to write the equation of the tangent line. So make sure you can visualize what's going on here. I don't really know what the function f looks like. I really don't. I don't know. I'm drawing it kind of like it's a cubic. No need to actually be a cubic. But I'm trying to figure out, let me put it in red. I like drawing tangent lines in red. I have no idea why, but I want to find out the equation of that line. I instruct my students that every time you're looking for the equation of a tangent line, which is something you certainly do a lot in calculus, to write down the general form of a line. Y minus y1 equals m times x minus x1. The point of tangency, well, that's going to be your x1, y1. And your slope is going to come from the derivative, f prime. So it's pretty easy. We know what x1 is. It's 5. We actually know what m is. It's the derivative at 5. So that's just 55. Now the real question is what y1 is. But don't forget, the whole real purpose of this equation is to give us the y value if we know the x value. Sorry about how messy that is. But I'm going to just go right up here. I'm going to figure out what f of 5 is. And of course, f of 5 is going to be 5 squared times g of 5. And that's going to be 25 times g of 5, which is negative 2. And that's going to give us a y1 value of negative 50. So I can now say the equation of my tangent line is y plus 50. Remember, I'm getting that because I'm doing minus negative 50. Equals 55 times x minus 5. There we go. All right, don't ever forget to answer the questions that are asked. Let's take a look at exercise 3. It says, for the function defined by y equals, and I'm not going to even say this function out loud. I'd like you to look at that and think about how you interpret that. But they give us this weird looking thing, f with a 2, and then they ask us which of the following would represent dy dx. Pause the video for a moment and think about how you might use the product rule to come up with this derivative. First thing you have to do is understand that notation. Okay, did you think about it a little bit? This notation should look vaguely familiar to you. In previous courses, hopefully, you saw things like this. Sine squared of x, which you should have known was sine x times sine x. Likewise, we can think of y as being f of x times f of x. And now we can definitely use the product rule. dy dx, take the derivative of the first function, f prime of x, times the second function, f of x, plus the derivative of the second function, which also happens to be f prime, times the first function, f of x. Of course, those two are the same, so I can gather them up as like terms, and I'll say that it's 2f of x f prime of x. Excuse me for switching the order on these two things, but I wanted to make sure that it looked like one of my 5 choices. Alright, let's go on and do the next exercise. Actually, not the next exercise. Let's talk about the quotient rule. Sometimes I joke with my students, the only thing nice about the product rule is that it's not the quotient rule. Take a look. The quotient rule will allow us to find the derivative of the quotient or the division of any two functions. And it is a beast. Take a look. It says that if we're finding the derivative of f divided by g, we can find the derivative of f times g, so the derivative of the top times the bottom, minus, really important here, the derivative of the bottom times the top, and then there's this weird thing, all divided by the denominator squared. Ugh. Little note before we go on and actually use the quotient rule. Unlike products, quotients are not commutative. So you would not expect the quotient rule to have a lot of commutativity built into it, and it doesn't. Unlike the product rule, that subtraction in the numerator, boy is that important. Because if you reverse the order, your derivative will have the opposite sign that you want it to have. Given that derivatives are used to talk about whether functions are increasing or decreasing, that would be a real problem. So let's jump right into exercise 4 and do some quotient rule. Alright, one nice thing about the quotient rule is that we can motivate it right now. There are functions, and letter A is a good example, that would be very hard to find the derivative without the quotient rule. So the quotient rule says, let's take the derivative of the numerator. That's a nice constant 3 because it's linear. And then we multiply it by the denominator. And we subtract off the derivative of the denominator, also a linear function, so its derivative is a constant, right, times the numerator. All divided by the denominator squared. That's the calculus. Everything after this is simplifying and it's algebra. So you should be able to simplify that numerator, and eventually the numerator comes out to be a constant. It's 7. Now, it would be very understandable if you thought you had to multiply out that denominator. Other calculus teachers may very well disagree with me on this, but I think I have hardly ever seen a situation where it makes sense to expand or multiply out that denominator. Don't get me wrong, I'm sure there's probably something out there where it's a good idea, but I find 9 times out of 10 it's actually quite helpful to not have it expanded. Alright, now I know we've only done one exercise, but why don't you pause the video and see if you can find the derivative in part B of that function using the quotient rule. Be careful. Try to simplify the numerator, but again, don't feel the need to square out the denominator. Pause the video now, maybe even take up to 5 minutes to try to find that derivative. Okay, let's see how we do this. G prime of x. We'll take the derivative of the numerator. Always the derivative of the top first. That's just 4x. I'm going to try to be careful in this problem because I've got these binomials going on. I want to be careful about my use of parentheses. So the derivative of the top times the bottom, minus now the derivative of the bottom, 3x squared plus 1, times the top, 2x squared. Again, these parentheses, which are oftentimes forgotten by students, are critical. The denominator ends up just being x cubed plus x quantities squared. Again, that's the calculus. Everything after this is just algebra. So distributing and combining like terms in the numerator, you eventually get negative 2x to the 4th plus 2x to the 2nd, all divided by x cubed plus x quantities squared. If you didn't get the numerator to simplify that way, spend a little time right now and take a look at your algebra. Alright, last problem. Here we're going to do a little bit of application. You're going to need your graphing calculator in letter D, so maybe grab that if you don't have it out yet. Here we're given a relatively simple function, f of x, and letter A it asks us to find f prime. Pause the video, take whatever time you need, maybe up to 5 minutes, and try to find f prime of x using the quotient rule. try to simplify the numerator, but leave that denominator alone once you have it in that squared form. Pause the video now, see what you can do. Alright, let's take a look and see how it's done. Alright, f prime of x. We're going to take the derivative of the numerator. And that's going to be a nice constant 40, right? The derivative of a linear function is just its slope times the denominator, x squared plus 9. Oh. Minus now the derivative of the denominator, 2x. Right? That plus 9 goes away because its derivative is 0, times the numerator, 40x. All divided by the denominator squared. Again, that's the calculus. That's it. The rest of it you've got to be able to clean up on your own. The numerator eventually simplifies to negative 40x squared plus 360. And we'll leave that denominator exactly the way it looks. X squared plus 9, the quantity squared. Alright, take a look at letter B. Letter B asks at what x values is f prime equal to 0? You've seen this before. Pause the video for a second and think about how you would find the x values where f prime is equal to 0. Alright, did you do it? Did you solve for x? If not, pause the video again. Alright, let's take a look. One of the beautiful things here is that our derivative is in the form of a fraction. And one thing we hopefully know about fractions is that a fraction will only be equal to 0 when its numerator is equal to 0. So we're solving actually a relatively easy equation. Doing a little bit of algebraic manipulation on this, we would eventually get x squared is equal to 9 and x equals plus or minus 3. Alright. Letter C asks us, what type of tangent lines does your answer to part B indicate? Well, if f prime of x is equal to 0, right, that means our tangent lines have slopes of 0, right? Slope must be equal to 0. Exclamation point. And that means we must have horizontal tangents. Make that look like an E. Now, the last part of your question just asks you to use your calculator to sketch the function in the standard viewing window. So that's like the standard zoom, negative 10 to 10, negative 10 to 10. Pause the video for a minute, put that into your graphing calculator, sketch it, and let's verify that we've got those horizontal tangent lines at negative 3 and 3. Alright, do you have a nice sketch? Shouldn't be too bad, right? Our function, when sketched in that standard viewing window, looks kind of cool. You probably have not played around with a function before that looks exactly like this. Whoops, missed. It actually goes to the origin, contrary to what I had. And right here at negative 3, and right here at positive 3, change this to red, we've got horizontal tangents, places where the slope is 0. Alright, that's it for this lesson. Until next time, keep thinking and keep asking questions. Every time you do, you'll become a better math student. Take care for now.